Have you ever seen or used an acetylene torch? Acetylene, as we see here, is one of our most common alkynes. Remember from earlier, an alkyne is a class of hydrocarbon that contains carbon-carbon triple bonds. Now, acetylene is used in torches because when it's combusted, it produces a very hot flame. This makes it very useful for a variety of different welding applications that we get with our acetylene torches. Now, of course, combustion is an example of a reaction that we saw with alkanes, and as we see, it also occurs with our other hydrocarbons as well. Alkynes also occur in some different natural products as well, although they are somewhat rare, and we do use them in the organic laboratory as well. So acetylene itself is actually very useful because we can build a variety of larger carbon-based structures just starting from the simple 2-carbon alkyne. So in order to understand these different functions and roles of alkynes, of course, as usual, we're going to go through the naming of alkynes, the general properties of alkynes, and finally take a look at some of the key factors that will impact the reactivity of our alkynes. As we've seen with our previous functional groups, one of the key things that we need in order to name a functional group is some kind of suffix to indicate the presence of that key functional group. For alkynes, as we see here in our name, our suffix is going to be a YNE. So all alkynes will end with YNE. If we have something like acetylene, this would be a 2-carbon alkene. That gives us our F prefix. So the IUPAC name for acetylene would be ethyne. Combining again the number of carbons as indicated by a prefix with that suffix indicating our functional group. As usual, if we have larger structures, we need to indicate the position of our alkyne using a number. Right, so in this case we have our alkyne over here. So alkynes are going to be linear due to their sp hybridization. So that's why I've drawn this in a straight line. We still have a carbon at every point where our bond changes. 1, 2, 3, 4, 5, 6, 7. We have 7 carbons overall. That makes this a heptyne. And of course, our alkyne starts at the 2nd carbon, so this would be 2-heptyne. Now, of course, if we have multiple functional groups in the same molecule, such as our molecule shown here, we need priority rules to tell us which one to give our lower number to. So for our alkynes, we have equal priority to our alkenes. And of course, that means we are also still less than other functional groups like alcohols. In the case of a tie between an alkene and an alkyne, the alkene will break the tie. So, in our example shown here, if we count from the right side, 1, 2, 3, 4, 5, 6, 7. This is still the same 7-carbon structure that I had before. But we should also number from the left side, just to compare. And we see that when we're numbering from the right, we get 2 for the position of our alkyne. We're numbering from the left, we get 3 for the position of our alkene. So since our alkynes and our alkenes are equal in priority, we're going to take our pink numbering system that gives us the lower number overall. If our alkene was shifted over, as shown here, this would result in our alkene being numbered with a 2, and our alkyne would receive a 5. Right? So if there's a tie, right, the pink gets 2 and 5, and the orange scale gets 2 and 5. The alkene breaks our tie, and we label the alkene with the lower number. But if one of them occurs first, such as in our previous example, we just number whichever one gives the lowest number to the first double or triple bond. So in the case of our structure shown here, our name would be hept, based off of our 7 carbons. And then we would break this up. 2-ene to indicate our alkene here at the 2nd carbon. 5-ine to indicate our alkyne here at the 5th carbon. Again, that lower number going to our alkene in this case, since we have a tie. Now in the case of our alkynes, we also have an additional classification we can use beyond our standard IUPAC nomenclature. And this is either terminal or internal. So an internal alkyne is an alkyne that sits inside of our carbon chain, right? So it has bonds to carbons on either side, and it's in the middle of our sequence of carbons, such as our peptide shown here. A terminal alkyne, on the other hand, is going to be at the end of our carbon chain and will have bonds to at least one and could have a second bond to a hydrogen. So our acetylene or ethine is an example of a terminal alkyne. So terminal alkynes are always going to be at the end of our carbon chains. In this case, of course, our carbon chain is only 2 carbons, so it's actually at both ends of our carbon chain. Next, we'll take a look at the physical properties of our alkynes. Now, of course, our alkynes are very similar to our other hydrocarbons, right? They only contain carbon-carbon bonds, which are purely covalent, and carbon-hydrogen bonds, which, although technically slightly polar, the electronegativity difference is so small that we usually just consider them as purely covalent bonds. So because of that, again, we're only going to have our London dispersion interactions, or van der Waals interactions. And so this means that we will have low boiling points, low melting points, and of course, low solubility in water. These properties are really shared for all of our hydrocarbons, right? So if you compare an alkene, an alkane, and an alkyne, they're all, if they have the same molecular weight, they'll all have relatively similar boiling points, melting points, and solubilities. Of course, as always, these factors are always affected by molecular weight. So again, you can have a very large alkyne that might have a higher boiling point than a small alcohol, or vice versa, right? The molecular weight will always affect this, but assuming similar sizes, you're always going to be seeing lower boiling points, melting points, and solubilities for your hydrocarbons, including alkynes. Next, let's consider the reactivity of our alkynes. So of course, as we've already mentioned, combustion will occur for our alkynes just as it does for other hydrocarbons, right? Alkanes, we talked about combustion extensively. Alkenes, we didn't really mention it, but it will occur there as well. Alkynes, things like acetylene, of course, burns with that very hot flame that we use in welding. But what we really want to look at for alkynes is going to be the unique properties of this triple bond and how that will affect our reactivity. Now remember, with our alkenes, we mentioned that we have this kind of high electron density here because of all the electrons in these pi bonds between our 2 carbons. So with our alkyne, we now have 6 electrons instead of the 4 for our alkene, and we have a very electron-rich center here between our 2 carbons. So that makes this somewhat nucleophilic. And if you remember, our alkenes, of course, use those nucleophilic electrons, the extra electron density between our carbons, in a variety of different addition reactions. So our alkynes will also do addition reactions. And in a lot of cases, these will be very similar to our alkene reactions, but we'll just be able to go one step farther because of the extra electrons and the extra bond here between our carbons. So we'll see a lot of similarities to our alkene reactions, but then we're going to extend them one step beyond what we normally see using the extra electrons here. Now the last general reaction category that we'll look at for our alkynes is actually an acid-base reaction. So if we react our alkyne as an acid, right, so we're going to be pulling off this hydrogen, so we break our bond between our hydrogen and carbon. That would give us a carbanion, where we have a negative charge on our carbon, and of course then we have our H plus that would be taken by the base. Now if this were to occur, at this point we have our carbon here. Remember, this is an sp hybridized carbon, so it has those two sp orbitals, and then of course all of the p orbitals, which I'll draw here in pink. So we have one going up and down, and then one going backwards and forwards in the z-axis, right? Remember, wedge coming out towards you, dash going away from you. So we have our p orbitals and our sp orbitals. So notice, of course, in this case, we would have one sp orbital bonding to our other carbon, and the other sp orbital would actually get that lone pair of electrons after our carbon reacts as an acid. Now, when we have electrons sitting in an sp orbital, so you should notice with our hybridization here, an sp orbital is actually much closer to an s orbital compared to sp2 or sp3 orbitals, right? So just think about it in terms of how we make that hybrid orbital, right? In sp3, you take one s orbital and three p orbitals, and you're mashing them together to make your orbitals, right? So essentially it's 3/4 p and 1/4 s. In this case, we just took one s orbital and one p orbital, mashed those together. So essentially this is half s and half p. Now why do we care about that? Well, remember, an s orbital is just kind of a spherical orbital right around your nucleus. So that means your electrons in that orbital sit closer to the nucleus, which makes them more stable, right? We always fill up those closer orbitals first, and then we fill up the further away orbitals. This sp orbital is a little bit more like our s orbital, so that means our lone pair will be sitting a little bit closer to the nucleus, and will actually be more stable here in an sp orbital compared to an sp2 or an sp3 orbital. So what are the consequences of this electron pair sitting in an sp orbital? Well, what this actually means is that the acidity of our alkynes is going to be greater than alkenes and also greater than alkanes. Now, of course, this would only be terminal alkynes because, if you remember, an internal alkyne only has carbon-carbon bonds, and so it doesn't have any hydrogen to donate. So if we're comparing our alkynes, alkenes, and alkanes, remember that acidity increases with the stability of the conjugate base of your acid. And as we just discussed, our lone pair here on the alkyne in an sp orbital is more stable compared to a lone pair sitting in an sp2 orbital or a lone pair sitting in an sp3 orbital. Now I should clarify, just because our alkynes are more acidic than alkenes and alkanes does not mean that they are strong acids. Right? So if we add water, and we want to try to react water with our alkyne, our water is not nearly strong enough as a base. So we can't use water to deprotonate our alkyne. We could put what we think of as a strong base, our hydroxide ion, and we could try to deprotonate it with a hydroxide ion. But our hydroxide ion is also actually not strong enough. Our reaction would strongly favor the reactants with our hydroxide ion and our acetylene, and we'd get very little of our product, acetylene carbanion, forming there. So in order to deprotonate our alkyne, it actually requires an even stronger base, and we commonly use amide ions, where we have a nitrogen with a negative charge. Remember, negatively charged nitrogens are more reactive than negatively charged oxygens because they're less electronegative and more willing to give away those electrons. So now we'd be able to come in and take that hydrogen and produce actually a significant amount of our carbanion conjugate base. Now once we've formed our carbanion conjugate base, we have some interesting reactivity here for this particular carbanion. Right? So we have a negatively charged carbon that's going to be basic. It's also going to be highly nucleophilic. Right? So we have a very strong base and a very strong nucleophile. Again, of course, since this was a strong base, we had to use an even stronger base to produce it. Right? That's why we couldn't use hydroxide ion, because even though hydroxide ion is a relatively strong base, it's actually not as strong as our carbanion product here. Now, of course, when you see strong nucleophile and strong base, that should make you think of SN2 and or E2 reactions. So we're going to have new reaction possibilities from this carbanion due to its strongly nucleophilic and basic characteristics. So one of the things that we can do with this nucleophile is we can do an alkylation reaction, which it follows a SN2 mechanism. So remember, SN2 mechanisms will dominate when we have strong nucleophiles and uncrowded conditions. So if we bring in an alkyl halide that is uncrowded, such as our bromopropane here, we can take our strong nucleophile and we can attack the carbon that's attached to our alkyl halide, right? This would be our electrophilic carbon. We can break off our halogen as our leaving group, and we can produce an alkylated product from our initial alkyne. Alkylation, of course, alkyl refers to a carbon-based branch, and so in our alkylation reaction we're going to be adding carbons on here. Our end product would be our alkyne, but then we form a new bond from our alkyne to our carbon here. So we'd stretch out a bond here, and then we'd have our 3 carbons now attached to our alkyne. And of course we also release our bromide as our leaving group. So this reaction can be used in order to add on a variety of different carbon-based structures to our alkyne. Now again, if we want to perform this alkylation, this SN2 mechanism, it does require an uncrowded reactant. So we have to have a primary or a methyl alkyl halide. If we have secondary or tertiary alkyl halides, then we're more likely to see that E2 reaction because, of course, in that case, our basic nature dominates, and we prefer to just do that E2 reaction to produce another alkene. So to sum up our alkylation reaction, we can take any terminal alkyne, right, because we have to have that slightly acidic carbon-hydrogen bond. We can react it with our strong base. Usually we're using our amide ion, so here I have sodium amide with my sodium counterion and my amide as my strong base. This will deprotonate it to form my carbanion, and then I can add my alkyl halide in a second step. So I want either a primary or maybe a methyl alkyl halide. So here I have methyl bromide. My bromide is going to be breaking off as my leaving group, and I'll add on that single carbon here. So there's my new carbon, there's my bromide leaving group, and of course from my original base I would still have my sodium counterion as well as my ammonia, NH3, that's produced when my amide ion takes that hydrogen. Again, if I have a secondary or a tertiary alkyl halide, so let's say we have 2-bromobutane, or 2-bromopropane rather, So here we would tend to react in a E2 reaction because of that extra crowding here, and so you would actually produce an alkene, and you would just reproduce your original alkyne. Right, so the alkyne would be taking that beta hydrogen and eliminating your bromine to make your alkene. So generally we're going to be trying to avoid the E2 pathway, and we're going to be emphasizing our SN2 pathway over here in order to produce our alkylated product. Alkylation in general is a very useful reaction because it's one of the few reactions that allows us to make new carbon-carbon bonds, right? So we can take small hydrocarbons, even as small as our acetylene, and we can use alkylation reactions to build it up into much bigger carbon-based molecules.